So hello everyone, now we are going to discuss definition of set closed under scalar multiplication with some examples. As discussed previously, for set closed under addition we need two elements of the set S. So here for scalar multiplication we need one element of a field and one element of set S, and in our syllabus that field will be what? Set of real numbers. So now we will go for the definition. So set S is said to be closed under addition if we take any element of R and any element of S, then their multiplication again lies in S. So if this is happening, then we will say that this set is closed under scalar multiplication. So let us see the first example. Now we have to take any element of R. So in particular I will fix my value of I will fix my element of R as 0. So over here 0 belongs to R and I have to take one element of set S, but you already know our set contains only one element, so I have only one choice, that is 1 only. So 1 belongs to S, but the multiplication, that is what? 0, which is not present in S. So therefore this is not closed under scalar multiplication. So here again I am giving a counter example in order to show that the set is not closed under scalar multiplication. Now coming towards the second example. So in the second example also I will use the similar logic. Now we are free to take any element of R. So over here I will take it as 0 again only. Why I am taking 0? Because our simple observation is that this set does not contain 0. Okay, and now you can take any element of S to give a counter example. So I will take it to be 3 belongs to S, but the multiplication is again 0, which is not present in S. So therefore this set is not closed under scalar multiplication. Now we will go for the third example. So third is also a similar one, because again it is an interval and this is not containing 0. So naturally I can go with the similar logic. So 0 belongs to R, and over here which element to take? I will take 3 only. You can take any element from that interval, but again 0 does not belong to S. So therefore it is not closed under scalar multiplication. Now what about the fourth example? It is interesting now. See, now this set already contains 0, right, over here. So now I cannot take my choice of element of R as 0 over here. So I need to pick some other element in order to give a counter example. So I have to pick such an element of R and such an element of S, that is this interval, such that the multiplication will go outside of this interval. Okay, so this interval is nothing but what? It is close 0, open 3. Okay, so I will pick some bigger number, because you know this set is a bounded set actually. So if I take large value of R, then it will be large value of some element of real number, then it will be easy to give a counter example. So I will pick 100. So for 100 belonging to R, and you can take any element of this set, I will take it to be 1 only, but what is the multiplication? That is 100. So is it present in S? No. so therefore this is also not closed under scalar multiplication. So the next example again I will leave for homework, you can do it. Now coming to the next example, that is singleton 0. So over here you can see that if I take any element of R, okay, I will call it as alpha only. Now since our S contains only one element, so naturally I have to choose 0 only over here, right? Now you can see if I multiply them together, I will get 0 only. So that 0 is present in S, right? And what can I say then? See, indirectly what I have proved, that if you take any element of R and if you take any element of S, why I can say any element of S? Because S contains only one element, that is 0. So this indirectly I am proving for any element of S. So if I take any element of R, any element of S, the product is 0, which is present in S again, so therefore this is closed under scalar multiplication. So what about set of integers? So for set of integers also, so smart choice should be there. Over here see, I will pick my element of real number as somehow, because you know how do elements of Z look like, and if I take 1 as element of Z, okay, you can see what is the product. Product is half, so that is not present in Z, right? So therefore this is not closed under scalar multiplication. Again, see, this thing will come by practice to you. Once you will practice for more examples, then you can easily understand whether the given set is closed under addition or closed under scalar multiplication or not. Okay, now for the next example, that is set of rational numbers. See, actually I will pick a element from R that is outside of this given set. That is the logic actually. So if you see everywhere, the same thing I am doing, right? So over here, outside of Q, in the sense I will think of what? Under root of 2 belonging to R, and you can take any element of Q of your choice. I will take it as 1, and you can see what is the product. The product is under root of 2, which is not present in Q, so therefore it is not closed under scalar multiplication. Now for the last example, that is set of real numbers, that is very clear now. So if you take any element of R and any element of S, now our S is also R, note this, and this is going to imply that this multiplication belongs to R only, because we know product of any two real numbers is again a real number. So therefore this set is closed under scalar multiplication. Now note one thing that I would like to tell you. Over here, whatever addition we have seen and whatever multiplication we have seen in this all examples, this is usual addition and usual multiplication. What do you mean by usual? This we have studied from first standard, right? So therefore it is called as usual addition and usual multiplication, right? Now this addition and multiplication cannot be usual always. Sometimes it can be matrix addition, sometimes it can be addition of sequences, sometimes it can be addition of functions also. Okay, that operation we are calling it as addition. Okay, Similarly, the scalar multiplication also may not be usual multiplication. It may be scalar multiplied by a matrix, scalar multiplied by some sequence, and what so on. So in the next class we will see a definition of vector space. So thank you.